Today we're going to talk about predictability and forecasting of the weather and climate. And there's a quote of relatively eliminated the Newtonian illusion of absolute space and time. Quantum theory eliminated the Newtonian dream of a controllable measurement process, and chaos eliminates the Laplacian fantasy of a deterministic probability. Basically, what this is saying is chaos, or chaos theory, removes, as you go further out from the starting point, the ability to predict. Once everything starts to break down as you get further from the origin point, because things aren't deterministic, they aren't set in stone. It doesn't follow A to B. It can go A to C or A to D. It can bounce between different possible solutions. So there are characteristics of chaos and what causes chaos in our prediction efforts. They start off with basically there's a limit to how precisely we can observe the atmosphere, or any system really. Basically, short of observing every single molecule constantly at every time step, you can't, and even that wouldn't be sufficient. But basically, if you're not doing that to absurd precision and accuracy, you will have issues with the level of precision at which you're observing any system. And again, along those lines, any prediction effort will be sensitive to initial conditions. So and I'll show you an example of this in a second. But basically, this is the butterfly effect. So a minor difference in the initial conditions. So it's a degree warmer, or not even a degree, a fraction of a degree warmer, impacts your ability to predict down the line because it's slightly different and it throws things off. And then nonlinearity, basically the assumption that everything linearly follows and goes from, like I said, A to B. It can ramp up. It can have exponential responses. And that has huge impacts on weather prediction. So like I said, we'll talk a little bit about the butterfly effect. And a great example of this is iterative quadratic difference equation, which is just a fancy way of doing this math. Take a number, subtract 2, square the result, repeat. And if you start with two similar numbers, 0.5 and 0.5001, and run through 20 iterations, you can see even 10 iterations, they're pretty close. But you get up to 20, and they are massively different. And in prediction models for the weather, equations like this are happening constantly. They are happening millions of times for every run of a prediction model. And that means minor differences in the initial condition throw things off. Now, obviously, we've gotten reasonably good at predicting the weather out to a certain degree, but that's within like a week or so. And then you see people coming out with things like 40-day forecasts. And this shows why that's not super accurate or particularly good, and often is wrong. So when we say it jumps between these solutions, we can think about this in sort of a phase state or phase space. And we can find those sort of solutions as attractors. So a good example of this is a pendulum. You know how fast it's swinging and where it is, and you can see that here. Basically 1 goes to 2, goes to 3, swings back to 4, and eventually it arrives at 0. And you have the location and velocity. And you can see plotting the velocity and location basically goes 1, 2, slowing down 3, slowing down 4, and it eventually reaches 0. And that 0 point is an attractor. This is a really basic example, but this is really important for predictability because, again, these attractor points, these solution points, are really, really important to find. And if you're bouncing between two of them, that tells you you're not sure of what you actually will forecast. So You can see these in your life, like a drippy faucet where you go drip, drip, drip on a steady timeline. That's a solution. That's basically a consistent wavelength. You can predict it when the next one's going to come. But if you increase the flow a little bit and you get drip, 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 you're changing it. And that's called period doubling, which is sort of discovered by Robert May, a biologist. It basically was looking at population and growth parameters. You can see that here, where it's basically doubling to a single one, to 2, to 4, to 6, to 8, to 12, and you can see the amount of information, or 8 to 16, you can see how much it changes and how difficult it is to determine exactly where you would be based on the increased flow rate. You can look at this as like waves added together. So again, you have, starts off pretty basic. Oh yeah. But as the waves adjust and as the wavelengths of those superpositioned waves impact, it immediately starts bouncing around and becoming much more chaotic the further you get out from the starting point. So, like I said, Robert May was sort of a biologist studying population growth. He was kind of confused because he was trying to predict, and he was seeing, oh, it bounces out, and then you get one solution. Okay, that's pretty good. But as further you go out, it bounces between 2, and then bounces between 4, and then 8, and then 6, and then it's doubling. And eventually you get far enough out, and you have effectively no idea what solution is viable or correct, because again, you're far enough out that they've doubled to the point of just being completely filled in. Anything within this range could happen, theoretically. You're not sure which one is realistically going to happen because of this, again, period doubling, population increase. In the same way, those growth patterns could create sort of complex structures as you get further and further out. There are games that can create fractals like this picture through geometry, through simple rules. If you go through the slides, you can see some of the games, you can see some of the indications on how these things can come about. You can try some of them out, you can look them up. Now, what does this have to do with forecasting? Well, again, forecasting revolves around pretty simple rules. And again, you want to solve for those rules, these differential equations, to describe the atmosphere's behavior. Basically, you simplify it down to three simple rules. And then you go to 3 decimal places. So again, and you basically try to use this and determine whether or not forecasting the weather is possible. And Ed Lorenz, one of the discoverers of chaos theory, or the butterfly effect, basically said long-range weather forecasting is impossible. We can go out 5-7 days. I believe the theoretical limit is around 2 weeks. So again, when you see people with 40-day forecasts, they're not particularly useful. But again, when the actual program was run, it resulted in diverging solutions. Basically, it bounced between entirely different or solutions that couldn't happen at the same time. And again, you can see sort of attractors. Basically, it's bouncing between 2 potential different solutions. It's bouncing between these 2 different things. So how do we deal with this? Like I said, we can forecast around to 7 days pretty realistically, and we're pushing that out, and we could get to the theoretical maximum of around 2 weeks. But we use probabilistic methods, Monte Carlo methods. I'm not going to get into exactly what those are, but there's one you could do at home. You could do the lagged average forecast. Basically, look at a forecast for next Saturday on Monday, Tuesday, Wednesday, Thursday, Friday. See how that forecast changes. See how quickly the confidence builds. So if on Monday it says next Saturday is going to be 50 and clear, Tuesday it says it's going to be 30 and snowy, And then Wednesday it says 40 and snowy and rainy. And then you get to a couple days in a row where it's like, oh, nope, it's going to be 40 and raining. The confidence has built. It eventually got to the point where it found a solution that it consistently worked with. And you can do this with your own forecast, with your own forecast data, and build the confidence in the forecast. And then one you can't do at home is ensemble forecast, which is literally just run the same forecast over and over and over again, finding what is the solution points, those attractors, and what seems most likely. What is the most likely outcome? And you can see that here. Basically, ensemble forecast, basically they run through a bunch of different forecasts and see what is likely to happen and build the confidence based on that. And again, you can see this is done with hurricane modeling. You can see that's why usually they give a cone of where they expect it. That's because different models say it will go in different locations. Again, you could have two entirely different solutions based on the model.